Now we are going to start discussing about the next topic, which was curvature. Okay, so just recall what we have done so far. We proved this formula to compute the arc length, isn't it? So we saw that the arc length of a curve is given by this integral. Okay, and then we defined this arc length function, which basically tells you that how to compute the length of a given curve between 2 points. Okay, the initial point, let's say the initial point and a given point. Okay, and we also saw that if I take the derivative, I am going to get just the modulus of r prime t. Okay, and then we understood this idea of parameterizing a curve by its arc length. Okay, now we move on to the second question, which was about the curvature. Okay, so the question was that can we measure that how fast the curve is turning, or how fast it is bending. Okay, so this is the question which we had, and then we want to understand, okay, how do we study this. Okay, so the notion to study this is called the curvature. Okay, this is the study of the bending or the turning or changing the direction of a given curve at a given point. Okay, so for example, I mean, these examples you already know, that if I have a line, okay, it doesn't change its direction, it has a fixed direction. So whatever notion we introduce, it should have that the line doesn't have any curvature, it should have the zero curvature. Similarly, if we look at circle, and you just draw a circle, and you will notice that at every point the curve is changing the same. So it doesn't have, like, at some points more and then the change is less at some other point. So that doesn't happen when you are moving along a circle. Okay, so these things, these intuitions should should be true when you give a notion of suitable idea to understand that how to measure the this change in the direction. Okay, so definition. Okay, let us start with the definition, and we see that how to compute it, and then where we can use it. Okay, so let us start. So here I have written a smooth, okay, which again it means that the derivatives and so on, they exist, because I don't want to write each time that derivatives exist and so on. So if I say smooth, you just assume that derivatives exist and then they are continuous functions and so on. Okay, so you start with a curve, and this notation S is the same notation as we defined in the previous class. Basically this is the arc length. Okay, so we are going to be consistently using these notations. So we have a curve, and then this is the arc length function or arc length parameter. So the curvature of this curve is defined by, okay, so what you do is you compute the rate of change in the unit tangent vector. Okay, so which is drawn over here. So think of this curve. Okay, this is the curve, and these directions, if you just recall the definition of tangent, these are nothing but the direction of the tangent vectors, and you take the unit tangent vector. So when you are moving along the curve, you see that the direction is also moving, the tangent vector is also moving along. Okay, so we basically capture, we try to capture the rate at which this is happening, and that is going to give us the curvature, the notion of curvature. So basically what we do is we compute the rate of change of the unit tangent vector. Okay, so this is over here, the t is the notation for the unit tangent vector, you know how to compute it, and rate of change with respect to the arc length. Okay, this is important, with respect to the arc length. So basically I take the derivative of this with respect to the arc length. Okay, so this is going to give me a vector, and you take the magnitude of this or the modulus of this. Okay, so this quantity is defined to be the curvature of the given curve. Okay, so this is evaluated at a point. So this is how you compute. Okay, so this is involving the change in the unit tangent, correct, how the tangent is moving. That is what these arrows are. So you see that here the change is small, you are just going in this, and then suddenly you see there is a huge change, and then again there is a huge change. Okay, so the rate of change is also going to be large over here. So we have to basically compute this or capture this. Okay, and now this unit tangent vector, you already know how to compute all, and derivative also you know how to compute. But sometimes what we have a curve given by its parameter equation. Okay, so we have to compute first t, and so now what we will do is we will try to simplify this formula in such a way that that involves only the position vector and maybe its derivative. Okay, so let us see that if we can write it, because here there are two things. One is that tangent comes, and then you have to take the derivative with respect to arc length, so you have to basically compute the integral also. Okay, so and this notation is called the kappa here. Okay, so this is not k, this is kappa. Okay, so let us see that what are the different looking formulas or the useful formulas we can have to compute the curvature. Okay, so yeah, as I said that we will try to express this formula in terms of position vector, and let us see. So the derivative, see, what we are doing here, we are computing the derivative here of the unit tangent. Okay, so but we are doing it with respect to arc length. So technically we would like to do it in terms of the position, okay, which is the t parameter. So just look at the derivative of the unit tangent vector, which is nothing but dt by dt. Okay, this is the vector. Now you use one of the properties of derivatives, namely the chain rule. Okay, so I can make a change. So I can, this dt by t, I can write dt over ds and then ds over dt. Okay, and this guy, you see, this involves the definition, this is involved in the definition of kappa, and this thing already, we had computed this is exactly this number mod of r prime t. Okay, so what I get, the derivative of the unit tangent vector is this times this number. Okay, this is number, but it depends on t. So what I know, this is kappa. So kappa can be written as in terms of the modulus, because you have to take the modulus of or the magnitude of t prime, and then this is anyway already modulus is there, so you have in the denominator. So here you have to assume that this is non-zero, otherwise it doesn't make sense. So whenever I write this and don't write that assume that r prime t is not equal to 0, that should be understood from the context. Okay, so now further we solve, and then we try to write this t prime also in terms of r. Okay, and I will have this small exercise for you, because this is going to be used. That t is the unit tangent vector, you compute its derivative and show that they are orthogonal. Okay, so this is always true no matter which curve you take. Okay, so the unit tangent vector is always going to be orthogonal to its derivative, and this you already know. This follows from one of the properties. If you recall that if you are moving on the sphere, for example, I had given an example. Okay, so all you have to do is take the dot product. Okay, and then dot product here, because this is unit vector, so you will immediately conclude. Okay, I don't want to give you the complete solution. Okay, so now we will try to write down this t prime also in terms of r. Okay, let us see. So basically we further solve it. Okay, and okay, this has been called as a theorem, and this says that the curvature at a point t can be computed using this formula. Okay, and you see this side, you just all you need to know what is r, and then you can compute its derivative, and there is a double derivative here, the second derivative. Okay, but this just involves the position vector. That is the important point over here. You don't have to do any integration or anything. Okay, so let us see. So as I said, all we have to do is, here we have to look at what is t prime. Okay, so let us do that. I already know that t is the unit tangent vector, because to compute t prime you need first t and write its definition. So r prime t is I know that r prime t is in terms of s is this. Okay, so you just substitute over here, what you get is r prime t is nothing but ds over dt times this. Okay, so now I look at the second derivative over here of this. So when I take the derivative further, there is a product over here. Okay, but you see this is a scalar function, this is vector. So we had a property how to compute the derivative of such product. Okay, this is not really a dot, this is a scalar multiple of a vector, correct? But both are functions. So I am going to get the derivative of this. So this gives me d2 and then the vector, and then plus it's going to be this function plus the derivative of the vector function. Okay, now I take the cross product of this vector and this vector. Okay, so what I'm going to get, the cross product of this vector and with this vector. Okay, now you see here I am going to use another property for the for computing the cross product. Okay, so if you recall, there was a property which said u cross v plus w, okay, is equal to u cross v plus u cross w. Okay, so I'm going to use that property, but here you see only one term. I mean, there should be technically two terms, so something is used over here. So the dot, I mean the cross product of this vector with this. Okay, now you see these guys are just constant, so they don't really play any role, they will come out. So what we have, the cross product of t with itself. Okay, and this is a small exercise again. You see that this is 0. So what you only get, you just get this cross product with this. So now this is scalar, this is a scalar, so you get a square of this, and then you get the cross product of t with t prime. All right, so I know that the cross product of this vector, these two vectors, is this. Okay, and now I compute the mod. Okay, so you see this side I have got now t prime. So if I compute the mod, I am just going to get, again you know that when you are computing the mod, I am going to get the modulus of this and then modulus of this, but t is a unit tangent vector, that means the modulus is 1. So then in the modulus, that t part will go away, only t prime part will be left out. Okay, so now this is, you know, this is giving me a formula for t prime in terms of this and divided by this, but this already is known to us. It can be written r prime t. Okay, so you just divide. We are dividing by r prime t often. I mean, we have assumed here that r prime t is non-zero. Okay, so basically you just substitute for t prime in the formula of your curvature, and then you get this. Okay, so the advantage here is that now you don't have to worry about any integration, you don't have to worry about anything. You just you know, get hold of the vector function, and then immediately at any point you can compute the curvature. Okay, so yeah, again I have written our favorite example over here. So all you have to do is just compute these derivatives. You know, this is just trivial now, and compute this. Okay, so this I have written here, please check whether this is correct. So what I am getting is that for the helix, the curvature is this. Okay, and you notice that there is no t over here. Okay, so that intuitively also you should look at the graph and then see that, you know, how, whether it is really a constant curvature or not. Okay, so please check. You know, these calculations, I may make a mistake here, but you must be very careful about these things. Okay, and I give you a few more examples here. Okay, they are called as exercise. So this is something which you already know. In your calculus course, you must have done something about it, that in your calculus you have seen curves in R2, isn't it? And I don't know whether you defined the notion of curvature over there, so but it's okay. I mean, if you did not, what you can do is you take a curve in R2. Okay, so the curve in R2 is basically graph of this function y equal to fx, isn't it? So x is a real number and y is also a real number, so this is going to give you a curve in R2. Okay, what you can do is you can think of this curve in R3 or in space by setting the third coordinate, the z coordinate, to be 0. Okay, so now what you have a curve in R3, and you know how to compute its curvature. Okay, so that's what you need to do here. So all you need to do is just write down the parametric equation of this in space. Okay, r equal to xt or ft, gt and ht. Okay, and when you do that and apply the formula which I just gave you, okay, this one, and you will see that the curvature is this, and this is exactly the formula which you must have derived in your calculus 1 course. Okay, so this, you know, this involves taking the second derivative and then first derivative, and this with this powers and so on. Okay, so please compute this and then match it with your calculus 1 formula, and you will see that this was exactly the same picture. Now the example which we started with, that, you know, this oops, this is circle, okay, this is not circle, this is circle, okay. So if I take a circle of radius a and apply this formula, you know the circles, I mean you have to write the parameters, and then you will see that the curvature is coming 1 over a. So you know intuitively also, if you think, if the radius is small, the turn is going to be more sharp, okay. If I take a huge radius, then 1 upon a is going to be small, that means the circle is turning very slowly, okay, very small turn is there. I mean imagine for example our earth, you know, if you think of it as proper spherical shape, you take any circle on it, like when we think of a road going along, we always feel that the road is flat, okay. This is because the radius is very very large, okay. So all these ideas are very important. They are, you know, used in computing, or you know, doing some real life problems, and that's how, you know, you study these problems, because they originate from some real life problems, okay. So solve a lot of examples. The book has so many interesting questions, so many interesting solved exercise and then unsolved exercise. So please do that. And you know, as I said, please be careful. If there you find any typo, just let me know, okay. And you don't have to be confused about it. I mean, until that this is updated, you can just go to the book, because just for this reason, that you know there's no confusion, no doubt, I am following this book which I have given you, okay. So everything is being taken from that book, with some possible change of language, and you know, maybe a little bit of a change of order also, but everything is there, okay. So there should not be any confusion, okay. Bye.